So I'm going to talk about a particular anisotropy that comes from quantum mechanics, and I will tell you what that is and why it's interesting, and there are some prior estimates of that. And the main part then after that of the talk will be to tell you how to do this on GPUs, because we recalculated it with fewer approximations, and then I tell you next steps and then we'll be done. So, okay, so I'm a heavy ion physicist, so we collide large nuclei together. Let me just move this over a little bit further away. Because we want to study a novel substance called quark-gluon plasma. So here are two large nuclei, they collide, moving left and right. Eventually, a small droplet is formed of this plasma. It's small, it's about 10 Fermi length scales, 10 to the minus 14 meters. And then in a fairly short time, this is about 10 to the minus 23 seconds, this expands, cools, breaks up to other particles because there is a phase transition. There are no more quarks and gluons after that, and particles that then fly to the detectors, and the experiments measure these. It's a complicated process with lots of different modeling that's happening on the theory side. I'm a theorist. But at the end, looking at the data and simulations, people infer that indeed there is a hot plasma that's being formed here about tero-Kelvin temperatures, and this behaves like a fluid, and especially it has a very small specific shear viscosity. Much of this deduction comes through an observable called elliptic flow. This is V2 is what refers to elliptic flow, because most of the time the collision is actually such that the two nuclei don't hit head-on, but they have an impact parameter. And that's why initially the system that's formed has this elongated cigar shape in coordinate space. What turns out that this coordinate space shape causes, at the end, when the particles fly to the detector, an anisotropy in momentum space. In fact, there are more particles moving in the initially short direction than in the other direction. And that's a dynamical effect which most models indeed have. In fact, the common interpretation is that this is all through fluid dynamics. Initially, the system has this anisotropic shape in space, but it has no anisotropy in momentum. Its V2 would be 0. But then dynamics continues. There are asymmetric pressure gradients here, and in the end, because there is simply larger force in the short direction, larger pressure gradients, you have more acceleration, you end up with such a momentum anisotropy. Spatial anisotropy we like to characterize through the eccentricity. This is just a measure of size difference between x and y directions. Okay, the square of those, but that's a detail. Momentum anisotropy becomes a dimensionless number because we do the same for momenta. The typical momentum in x direction minus y direction divided by the sum. It's also the average of the cosine 2 phi angle in this plane. So what people do then, they take this seriously, so seriously that actually very complicated simulations are being run to infer properties of this fluid via experiment, via comparisons to experiment, and people now want to push to few % precision in extracting, for example, the viscosity. Theoretically, however, there is a big question mark. How can I justify fluid dynamics at Fermi scale? And that's not understood. In fact, one worries that quantum mechanics should play a role. And here is a simple idea that we put out a couple of years ago, backup envelope estimate that there should be a problem. So imagine you have a quantum system in 2 dimensions. V2 is just this eccentricity in the dispersion of the system in momentum in between the x and y directions. So great, so just write this up. But if your system supposedly it's in the ground state, just for the sake of example, and we keep h bar 1 because that's a simple, we want to keep units simple, then these dispersions in momentum are related to dispersions in coordinate. In fact, they're inversely related. So the dispersion in the x direction is the inverse of the dispersion in the coordinate x direction. And the same for the y direction. It's missing. It's the wrong subscript. So in the end, you plug, instead of the momentum dispersions, the spatial dispersions, do 2 lines of algebra, and you find that V2 is as large as the initial coordinate space eccentricity, which is 30%, huge. This would suggest a V2 which is bigger than experimentally seen, without any dynamics. There was no hydrodynamics, purely quantum effect, wave effect. Now, of course, this is if the ground state plays a role. We are at high temperature fluid, so excited states also enter, life becomes more complicated, and also there should be expansion dynamics which affects this. In fact, ideally, one should somehow do hydrodynamics together with quantum mechanics, except we don't know how to do that. But we can at least investigate the same example at finite temperature. So let's do that. This is standard statistical physics. You can open Landau's book, and it's in there. I think it's volume 5. So if you take a simple gas, it's one particle in an anisotropic potential, so that's what gives you the anisotropic density distribution. Classically, you just do some integrals in phase space, you integrate the lower positions, so only momentum remains, you do the integral, and you find 0, because you end up with the exponentiating the kinetic energy that's perfectly isotropic. Our effect completely gone in classical physics, that's why people normally don't see it. It's not even, it cannot be captured by hydro either. But if you do it correctly, in quantum mechanics, you have to sum over energy levels. So instead of doing these integrals, you sum over all states of the system with a Boltzmann weight and put in here, in momentum space, the wave function squared. This sum is, in general, anisotropic, but it's hard to do, except in some cases, non-relativistic particle, two-dimensional oscillator trap, we can actually do this analytically, and in the end, after some calculations, which I'm skipping here, you find a non-zero V2, which depends on inverse temperature, inverse mass, inverse length squared, and it's proportional roughly to eccentricity. So this is a non-zero effect, but you see, if I send temperature to infinity, or mass to infinity, or size to infinity, this goes to 0. And that's the classical limit. Now, in fact, ignore the slide, it's too much physics here, but the statement I want to make, and if you're a physicist, you can check this at home later, the problem is actually fundamental. I have an anisotropy in momentum space, even though if you more carefully analyze the problem, I have no energy flow, no momentum flow. So hydrodynamics simply cannot capture this, because the fluid flow velocity everywhere will be 0. And it cannot give me V2 because it doesn't have this wave effect. Okay, so how large is this effect in actual experiment? You have to make an estimate. So you have to adjust the trap size and basically the trap parameters to give you a system which has roughly the size that we form in heavy ion collisions. We did this matching for gold-gold collisions at the relativistic heavy ion collider. This is V2 that we get from this effect as a function of impact parameter. For pions, non-relativistic calculation, it goes up to about 3%. This is percent scale. And then it drops, so it's a few percent effect. If you look in momentum space, it's even more exciting. So this is eccentricity. We pick 8 firm impact parameter and plot against the momentum of the particle. This is the pion elliptic flow divided by 10. This is actually 10 times larger. We just divided to fit on the plot. Huge, 10, 20% results you see here. Now, of course, criticism, which is valid, is that once you have high momentum, pion mass is about 0.14 GeV. This is non-relativistic non-relativistic calculation cannot be trusted at such high momenta. So we, lot of hard numerical work now, we redid this for massless particles, 0 mass. And we found the green curves, so it's smaller, but it's still about percent level, and the momentum the dependence is also totally different, but it's again a percent level. There is some anisotropy in here, which should be considered. But of course, the huge difference between non-relativistic and fully like basically ultra-relativistic calculation where the mass is 0 raises the question, so what about the real pion mass? So we'd have to put in energy, square root of m squared plus p squared. This comes from relativity, and you need to do this even harder calculation, which is now even more numerical. So this is what it would take to do that calculation. So you just simply take the Hamiltonian square root of, this is the kinetic term, and here is the potential, which is an anisotropic harmonic oscillator potential. For convenience, we chose parameters such that there is an energy scale mu and an anisotropy parameter alpha. But it's 2 parameters which control the potential in x and y. M is the particle mass. Now, if you're a physicist, you know this is really horrible, this square root. But they use some tricks. I don't want to do the tricks. You can read these, so-called canonical transformation. This problem is equivalent to this one. This is a non-relativistic particle in a funny square root potential. This is now finally doable on a computer as solving the Schrödinger equation. In the end, it's a little bit trickier, because what I need is I solve my problem, do all my thermal sums, find the size of the system in x and y directions, and then I have to adjust this parameter mu and lambda to what I want. If it's not the correct result, I have to redo the numerical calculation with new values, and I keep having iterating or at some point interpolating until I finally solve the problem that I want. But nevertheless, this life is hard, but one can manage. So in the end, I have to diagonalize the Hamiltonian. This is done in a finite basis. You expand the wave function over some basis functions, and then you plug it into the Schrödinger equation and express everything using these quantities, the expansion coefficients, and the energy eigenvalues. If you choose basis sets such which are not orthogonal, this is a so-called generalized eigenvalue problem. Lots of linear algebra packages can handle this, which is good because I didn't have to invent that. What matters is basically this is a matrix times a vector equals a number times another matrix times the same vector. And the matrices are known, the value is not known, and the vectors are not known. So I can actually calculate all these matrices with some effort. And indeed, for this complicated potential, I have to do numerical integration. And that's really the numerical part of it. One is to compute these matrices, which involves for this overlaps of the potential numerical integration. And then the second part is to solve the eigenvalue problem. And unfortunately, I am in a high temperature regime relatively. So when I do this sum, I need a lot of eigenvalues because this exponential doesn't drop very rapidly. I need thousands of eigenvalues calculated correctly. And I also need not just the eigen, because in some areas of physics, it's good enough to know the eigenvalue and you're done. I actually need the exact eigenvector as well because I need to square those to put into the sum. And to get such thousands of eigenstates correctly, I need much larger variational basis. So I'm basically doing, in the worst case, 100,000 states almost. And once I have this, I compute the anisotropy called V2 by simply taking the cosine 2 phi average of this momentum distribution. So naively, this is the cost. Matrix elements, there are about order n squared if you have a basis of n states. And diagonalization, we know it's kind of like inversion, it's order n cubed. So you see n cubed beats n squared, so you think at high n, you actually most of the time diagonalize, and indeed I have fairly high n. But the devil lies in the details. First of all, the coefficients matter too. In fact, depending on what algorithms you use, a small coefficient n cubed may be faster than a large coefficient n squared. So there's some discrepancy there. And indeed I do, because for my sort of bad luck, I discovered Intel's beautiful MKL packages, which run really, really quickly, and that's why the LAPAC routines that I use, once I use the Intel routines, are much, much faster. And indeed, what I found is that I spent more time in computing matrix elements. So partly also because when you compute the matrix elements, this just tells you how many matrix elements you need to compute. But if you have basis functions which are defined iteratively, then actually it becomes a higher than order n squared problem, because to compute one function at high order, you have to do iterations to get there. Okay, so I basically put the matrix element calculations onto GPU, which is in some sense a good problem for GPU. There's really little data. You send a bunch of integers, and then you get back two real numbers, the value of the integral and the error estimate. So that's really nice, but there is a bad part. These are integration routines. The best routines are usually adaptive, and it means that I don't know how many iterations will be taken. There are conditionals, and there are loops with some error condition in there. So it's not suitable in this sense for GPU, and I'm struggling with this still, but I've made some progress. Now, this is, you think, okay, it's some quadrature problem for quantum mechanics, but if you can do quadrature well on GPUs, it helps in other areas of physics as well. For example, I spent quite many years of my life doing 4-dimensional integrals for kinetic theory. And in fact, the only reason I did 4D because 5D was too slow. I actually really wanted to do 5-dimensional integrals. So if I can solve this problem, if somebody can solve this problem for me, I can solve more complicated physics problems in other areas of life. All right, so how do I do this? There are some tricks here. Let me just check how I am with time, because I might skip some of this. Okay, some still good. So the way I solve this is I choose basis. Basis is nice if it's factorizable. So you factorize either in x and y or in polar coordinates. It just keeps life simple. Then it means that when I say n basis states, I run n, for example, in the basis function in the x direction, basis function in the y direction, up to square root of n, which I will call capital M. So that's it. So I have m squared states. And there is also some little trick with parity. If you're a physicist, you can realize that there are actually 4 parity classes here because the potential is parity even in x and y. So it means that you can solve smaller problems 4 times, which does help with speed. And also some of your integrals become nicer because the limits on the integral are tighter, so you can get the integrals correctly with fewer points. I don't want to discuss that much because there's probably non-physicists as well here. In the end, we tried harmonic oscillator bases in x and y, but they were extremely slow because they are defined iteratively, and I had to iterate n times to get to a high-order harmonic oscillator. And I need these oscillators at different points because of my adaptive routines. They don't evaluate them always at the same point. So this is slow. It's good for cross-check. But in the end, we have 2D polar basis, which is much better. So in the phi angle, we chose two orthogonal systems, sines and cosines. This is a Fourier type of basis. And in the R direction, we ended up choosing localized splines. These are polynomials which live on a finite narrow interval. The reason we do this, because simple powers don't work. Mathematically, they would, but unfortunately, the problem becomes ill conditions because these powers overlap with each other for almost any power appreciably, and then it's an ill-defined eigenvalue problem numerically, so you get crap out. But these splines work quite well. So, first method. So I tried 3 different ways to do this. They're progressively better. One is just simply put those loops, what I showed you, onto the GPU as is. So every task on the GPU computes, every thread computes one integral for me. So this one nested loop. And we use Gauss-Kronrod quadrature, which is nice with 61 points. So of course, quadrature, everybody knows, is simply an estimate of an integral taking points at special location inside the interval with some special weights, and you sum them up. And it's 61 evaluations of the function. Why I like Gauss-Kronrod? Because with the same points, but taking only half of them, but different weights, it also does another estimate of the integral, which then it uses the difference to estimate error. So you in the end get a value and an error, and this is adaptive. So you first start with a full interval, do this estimate. If the estimate is not accurate enough, you halve the interval. Then you keep halving subintervals, always the one with the largest error, until you finally converge and your total error becomes small enough. And because of this, that you are cutting always the most promising interval for improvement, it means that it's adaptive, which is nice, but it's a nightmare if you think in terms of efficient GPU runs. So this is actually the sketch of the routine in one dimension, so just one, say, the innermost or outermost integral. So first you allocate some storage for where you will store these results for intervals and where these subintervals are, and you have to say how many you have. So dynamical memory is not something the GPUs are really great for. And then you integrate for the first interval, which is the full range. You get something. If the error is too big, then you start subdividing. Then you divide the interval into half, integrate over each half, update your total sum and total errors based on what you found in these subintegrals. You store some results, and you continue. If the error is still too big, then you have to go find the most promising interval and keep doing this until either your error converged or you ran out of space. You cannot store more intervals, and then you return with that. Both this loop is not very good for GPU. Also, here is a search, which is not that good for GPU. I actually did linear search. It's poor, but I didn't want to make GPU struggle. There's actually room here for improvement, but we haven't yet explored that. So, method 2. So it's clear that these iterations are really pain in the butt. So what you want is somehow to understand how many times you need to iterate, and if you could use the iteration number somehow not in a deterministic way and not in an adaptive convergence type of way, then you can make progress. And in fact, what we found is that the innermost integral, which is the radius, is 2/3 of the time only done once. And the other 1/3 of the time, it's done twice and never more. And I really computed millions of matrix elements. It never happened. So actually, it turns out to be factor 2 faster to simply say you always do 2 intervals and that's it. No logic, no iterations, nothing, just do the 2 intervals, which is actually 2/3 of the time and overkill. Nevertheless, it runs faster than GPU. Now, you would love to do the same for the angular integration as well, but the problem is, and this is different from the kinetic theory problem that I solved before in 4 dimensions, is that here you have oscillatory integrand. So you cannot easily estimate how many iterations you need. Here is an example. This is the potential, which I'm kind of integrating. It's a nice, smooth function, but I am multiplying it by the product of 2 angular basis functions. I just took a fairly low order, 25 and 39. In my actual calculations, I'm out there at 150 and more. And you see it's oscillatory, and there are pluses and minuses here, and in the end, this is some number, which is much harder to explore accurately. It's also clear that the higher order you have, the more wiggles you have, the higher order you will need. So the more iterations you will need to actually get this result, and that's what also makes the calculation of matrix elements slower than naively anticipated. And nevertheless, at least we save here by factor 2. And there is a third one, a really low-hanging fruit, is that you can also group the work better to the work groups in OpenCL. The code runs in OpenCL 1.2, and this is a feature that in OpenCL, when you start the tasks, then they are in work groups, and the work group is gonna wait until the very last task finished in that group. So your job is actually to, if you want to optimize, is to group tasks which run about the same length in time into one work group. And originally, this was how I assigned the task. I simply ran loops for one of the basis function, angular part, radial part. There are indices which tell you which function to choose. Then I run inside another loop for the other basis function, angular part, and radial part. And then I start this as a task. Effectively, that's what happens. So it means that the index of the task involves the angle at a low bits, in the low bits. It means that there are only very short contiguous ranges for tasks which involve the same n, which means they have roughly the same running time. But a very simple modification by swapping the 2 loops, by simply doing the angles outside and the radii inside, gives you a different mapping to indices of the task, and this is the task ID, if you wish. And now there is a huge contiguous range at the low bits which correspond to the same angular part, the same length in time. This gives me another 50%. So it's really simple what I did. This is actually some benchmark. So I ran at the computing center at Purdue, where I'm at Purdue, so this was sort of natural thing to do. And here at the GPU lab, I ran on something else, in the GPU. So this is a Xeon system, and the other one was just a development machine, a Vega 56, so it's not really a super fast thing. And this is what I find, runtime versus problem size. This is the m variable squared of n. This is CPU runs on 1 core. This is the first GPU run, and the first improvement, and the second improvement. This is log scale. So at least it looks like that the GPU could be useful. I'm definitely not using it efficiently, but I do gain compared to CPU cores. Of course, this Xeon has 20 cores. If I use those 20 cores and probably about 15 core equivalent I would get out of them for this problem, that would beat the first 2 runs and would be fairly comparable to the blue line. But at least the GPUs are not completely useless, and probably there is more room for improvement anyway. You could do relative to CPU. This is the basic algorithm. It's about maybe up to 6 times faster than 1 core. Let's call this a baseline. Relative to this, I want to do improvements. My first improvement, eliminating inner loop, was a factor 2. Relative to that, another 50% by just better scheduling. So that's where I am. These things haven't plateaued yet. Presumably at some point at high n, maybe these curves become more flat. I haven't yet explored that. But nevertheless, once I'm out here, my best case scenario, I'm about 20 times faster than 1 CPU core. So I'm comparable or slightly better than using all the cores on one box, one machine in the cluster. Now, what do we get in the end? So I go back to the quantum anisotropy. This was V2 as a function of impact parameter, non-relativistic result, massless result. And what I find is this is my new calculation now with the correct pion mass. The reason there is still an error bar here is because I didn't tune very carefully to the same impact parameter. So the trap is not exactly what I would love to. It will require more simulations. Also, at some point, I will have, of course, all the curve developed here, but it's very interesting, that even though now I have a much harder calculation and with the correct mass, I'm actually very close to the massless result. And this is not trivial because changing the mass changes all the eigenvalues, changes all the eigenfunctions, it changes my sums, but in the end, this is what I got. I don't yet have results for the momentum dependence. Perhaps it's similar, perhaps it's not. And also, I don't know the other impact parameter values, what I would get for that, but at least it suggests that maybe the blue curve will be slightly above or slightly below the green curve. Okay, so let me see where I am time-wise. Okay, so let's look at improvements and ideas. Now, of course, clear, I will do all the details of the calculation and I will get more results, and that's fine, that's uninteresting. How about just solving the problem on GPU? Well, I actually think that the biggest bang for the buck would be somehow to make these integrations deterministic to exactly know how many intervals and where I need to take. In fact, by thinking about this, I realized that I have double cosines and double sines, only these type of integrals are non-zero for my case, but you can pull a little trigonometry and you rewrite these products using single cosines. And then I have to analyze much simpler problem when there's only one integer. I have to study the properties of how this integral and how the cancellations go. But A, it's much simpler. My guess is probably I just have to integrate piecewise over each oscillation of the cosine. Even better, because these are indexed by two numbers, but in the end, only the sums and the differences matter. It means that instead of calculating m squared matrix elements, it's enough to calculate order m. And I save a factor 200 right here, which probably means that I actually don't need the GPU anymore because this part of the problem becomes irrelevant. It's very fast because I will save on calculation of matrix elements because I can assemble them from the integrals with just pure cosines. So in the end, everything points towards actually facing the diagonalization problem, which at high n will anyway dominate. But there is a problem. You would love to put this on a GPU, but with 500, the result is 30 gigabytes. The matrix is actually sparse, so I can push that on a GPU, but storing the result, the eigenvectors for this problem, takes 30 gigabytes of RAM, it won't fit. So in some sense, I will have to look at somehow GPU accelerated linear algebra, and I don't know anything about it, but if I want to solve this problem faster, then I will need to go in that direction. If anybody has tips on that, let me know. Okay, so we get to the end. So in the end, the main message of my talk was that even though a lot of people attribute momentum anisotropy, V2 in heavy ion collisions to hydrodynamics, that's not the only source. I believe some of it must come from quantum mechanics. We don't know how much, we can make estimates, and also we have absolutely no idea how it affects the dynamical evolution of the system afterwards. Simple estimates that we performed before suggest that it's about percent level in gold-gold collisions at the relativistic heavy ion collider. But these estimates varied by a factor 3 depending on what approximation one made, the massless one or the non-relativistic one. Here is now a calculation which has the correct relativistic kinetic term, and we find that the result is actually quite close to the massless case. So if I had to make a guess tonight, I would think that probably the massless result is closer to truth than the non-relativistic for ions. So there's some lessons being learned here. I ignore the physics part. The most important part for me, since this is a GPU workshop, is that adapting calculations to GPU, actually, in my experience, and it's not much, but that's what I have, requires you actually to rethink your problem so that you can adapt it and fit it to the GPU. And through this rethinking, you don't only learn about programming and optimization and so on, but sometimes you can actually get better algorithms for your CPU as well. Just like in my case, I think now the matrix element calculations will be super fast because I pulled a little trick in trigonometry. So let me grab, since this is the last talk, let me grab the opportunity to thank all the organizers, Gergely, Mate, and I don't know whether Dani is in here, and everybody else who have to put this very nice meeting together. It was also running very smoothly, which is an extra benefit, and the food was great. So thank you very much, and thank you for listening to this talk.
So, any questions to the speaker? Gergely has one, of course.
Dénes, one part, maybe I missed a point that if you would use another particle instead of pions, does it really matter? So does it make two?
Oh, it does. It does. Let me just get back to this plot. So this is the result for proton.
Aha, okay.
So actually it's hidden in this formula. I didn't go much, but the anisotropy is roughly speaking inversely proportional to the mass. So a heavier particle actually gets less anisotropy. So that's why we went for the lightest one for the pions. But we both of us know that pions are actually the most abundant in this collision. So that's probably not a too bad approximation.
And the other thing is a remark. If you would go to the before the last slide where you mentioned that the future perspectives, like, yeah. So, I mean, you know, we have these inter-axion phi's, which are maybe more suitable for this problem. So it has huge RAMs and the same number of processing units inside. So maybe that you can use that.
Yeah, I haven't thought of changing the hardware.
Yeah,
so
okay.
yeah, Gergely is right that I could move to perhaps better hardware which likes conditionals.
If you optimize this for GPU, then it will, you know, skyrocket on the...
I haven't checked FPGAs either.
Yeah, okay.
No.
Okay, so let's thanks Dénes again.